All right, welcome to the explainer. You know those tricky math problems that ask if a function is continuous? If you've ever felt a bit stuck on those, well, you are in exactly the right place. Today, we're going to break down continuity and give you a rock-solid strategy to absolutely nail these questions on your Class 12 board exams.
Believe it or not, it all boils down to a really simple idea. Can you draw a graph without lifting your pen? Seriously, if you can trace a curve from one point to another and your pen never leaves the paper, then you've already got the gut feeling for what continuity is all about. Okay, so here's our game plan. We're going to start with what continuity even is, then get into the 3 official conditions. We'll look at the different ways a function can be discontinuous, and then, this is the important part, I'll give you a checklist you can use to solve any exam problem we throw at you. Right, let's get into it. We're taking that simple pen test idea and turning it into a proper mathematical rule. So, at its heart, this is what we're talking about. A function is continuous if its graph is just one smooth, unbroken road. If there's a sudden jump, a pothole, or a bridge is out, anything that forces you to lift your pen, then it's not continuous at that spot.
But, you can't just write, "I didn't lift my pen" on your exam, right? So how do we make this official? This is where mathematicians came up with 3 very specific conditions. These are the rules you'll use to actually prove whether a function is continuous or not. And it all comes down to this one powerful little equation. All this is saying is that the destination you're heading towards, from both the left and the right side, has to be the actual location of the point itself. The approach has to match the reality. So that one rule really breaks down into a simple 3-part checklist. First, is the point even defined? Like, does a destination f of c even exist on our map? Second, does the limit exist? This means the road coming from the left and the road coming from the right have to meet up. And third, and this is crucial, does the limit equal the value? Are those 2 roads meeting up at the exact spot that was on the map? If you get a yes for all 3, you've got continuity. Okay, so what does it look like when a function fails one of those checks? When things go wrong, what kind of breaks do we see? Let's play detective and spot the different types of discontinuity. You're really going to run into 2 main culprits here. The first is a jump discontinuity. This is pretty obvious. The graph literally jumps from one level to another. The path from the left and the path from the right just don't line up. Then you have what's called a removable discontinuity, which is basically a hole. Think of it like a perfectly good road, but there's one single tiny pothole. The road leads right up to it from both sides, but that one specific spot is just missing. All right, let's get to the good stuff. This is probably the most important part of this whole explainer. This is your step-by-step method for tackling every single continuity problem you'll see. This is your checklist. It's 4 simple steps. 1, find the value of the function right at the point, f of c. 2, find the limit as you come in from the left, the LHL. 3, find the limit as you come in from the right, the RHL. And 4, compare them. Are all 3 values, the left, the right, and the actual point, exactly the same? If they are, boom, it's continuous. Simple as that. Okay, enough with the theory. Let's see how this checklist works in the real world. We're going to tackle some actual problems from past CBSE board exams. So here's a super common type of question. They give you a function that works everywhere except at one specific point, in this case, x equals 3. At that exact spot, the value is just k. Our mission is to figure out, what number does k have to be to perfectly patch that hole and make the whole thing continuous? Okay, first move, always try to simplify. That numerator, x plus 3 squared minus 36, that's just a difference of squares, right? It's x plus 3 squared minus 6 squared. So we can factor that into x minus 3 times x plus 9. And look at that. The x minus 3 on top cancels with the x minus 3 on the bottom. So this function is secretly just the line x plus 9 everywhere except at x equals 3. So to figure out what k should be, we just need to see where that line is headed as x gets close to 3. We just plug 3 into x plus 9 and we get 12. That's it. That's the value that fills the hole perfectly. For this function to be continuous, k has to be 12. Okay, next up. This one looks a little more intimidating because we've got a piecewise function and that absolute value sign. That's a classic exam trick. The game plan is the same though. We need to check the limit from the left and the limit from the right and see if they match up right at x equals 0.
Let's use our checklist. First, the left-hand limit. As we approach 0 from the left, x is a negative number, so the absolute value of x, modulus x, is actually negative x. That means our kx over modulus x becomes kx over negative x. The x's cancel, and we're left with just negative k. Now for the right-hand limit. When x is greater than or equal to 0, the function is just 3. So the limit from the right is 3, and the value at 0, f of 0, is also 3. For this to be continuous, the left has to equal the right. So negative k has to equal 3.
Which means, of course, that k must be negative 3. We just made the left side meet the right side, and that gave us the answer. All right, here we go, a trig problem. But don't let it throw you off. It's the same idea. We need to find the k that makes it continuous at pi over 2. Now, if you try to plug pi over 2 in directly, you get cosine of pi over 2, which is 0 on top, and pi minus 2 times pi over 2, which is also 0 on the bottom. 0 over 0. That's our classic signal that we need to find the limit, probably using a special trick. And the trick here is a clever substitution. Let's create a new variable, t, and set it equal to x minus pi over 2. Why do this? Because as x gets really close to pi over 2, our new variable t gets really close to 0. And we have some great limit rules for when things approach 0. After we do all the algebra with the substitution, the whole messy expression simplifies beautifully into k divided by 2 times sine of t over t, and we know that as t approaches 0, sine of t over t approaches 1. So our limit is just k divided by 2. We're told the function's value at that point is 3, so the limit must equal the value. K over 2 must equal 3, which means k has to be 6. And just like that, we've cracked it. The answer is 6. So let's recap the core strategy. This is what you need to remember. Step 1. Simplify. Always look to factor, cancel, or use an identity first. Step 2. Find the limit as you approach the point. Step 3. Set that limit equal to the actual value of the function at that point. And finally, step 4. Solve for whatever you're looking for, usually k. That's your game plan. And there you have it. That's how you can master continuity for your exams. But think about this for a second. This idea of fixing a broken function, of making things smooth and connected, isn't just a trick for exams. It's a really powerful idea that shows up all over higher-level math and science. So the question to leave you with is, now that you know how to do this, where else might this powerful tool be used?